In this video, we're going to introduce electrochemistry and redox reactions. You should already be able to identify redox reactions and assign oxidation numbers for elements and compounds, and by the end of the video, you should also be able to identify which species is oxidizing and reducing, as well as oxidizing and reducing agents, and then balance redox reactions in acidic and basic solutions. So first, electrochemical reactions mean that the electrons are transferred from one species to another. And in order to keep track of which loses electrons and which one gains them, we assign them oxidation numbers. And so really the difference is the charge and oxidation number are usually the same for an individual ion. But when you start talking about polyatomic ions, like SO4 minus 2, that minus 2 is the charge of SO4, but each S and O gets an individual oxidation number. And even elements, pure elements, which would have a charge of 0, will have an oxidation number of 0. So we'll go through the charges in a bit, but any element that loses its electrons will put that electron on another atom. You can't have oxidation without reduction. So oxidation is a loss of electrons and an increase in oxidation charge as you go, and reduction is a gain of those electrons or a decrease in the charge as you go through a reaction. So a species is oxidized when it loses electrons. So if you look at zinc, when it's alone, it has not reacted, it has a charge or oxidation number of 0. H had a +1 charge, zinc had a +2 charge, and hydrogen had 0 charge. And what you're seeing over time is that zinc lost 2 electrons to form zinc ions. And the reason is because it used to have its normal amount of electrons on the table, and protons can't change, so the only way to get a +2 and have more protons than electrons is to have lost those 2 electrons. Another way of thinking of it is that it means if its charge goes up, it oxidizes, and oxidizing is a loss. LEO, remember Leo and Ger? LEO, Leo means lose electrons, oxidation. And then a species was reduced when it gains electrons. So hydrogen here was +1, and then it became H2, it reduced its charge because it gained electrons. So Leo the lion goes Ger, gain electrons reduction, GER. So again, one element has to oxidize while another element reduces. So agents are probably not going to be on the exam, but I just want to put it out there in case you do see review questions from another source. An oxidizing agent is the one that's making something oxidize, just like a travel agent makes something travel. So in this case, hydrogen oxidizes zinc by taking electrons from it. And same thing for a reducing agent. So the travel agent doesn't travel with you, they make you travel, right? So a reducing agent is making something reduce. Zinc is reducing because hydrogen is giving its electrons. So in this case, if zinc is oxidizing, it's also known as a reducing agent. If hydrogen's reducing, it's also known as an oxidizing agent. They work simultaneously. So what the major thing that we have to be able to do is balance an oxidation and reduction reactions. And so if you can already assign charges, this would be great. So we're going to be reviewing that in our packet first. But after you assign your charges, you need to know how to balance a reaction. If you look at this, this is not really obviously easily to balance because even if you start playing with it and put a 2 in front of CO2, it might balance the amount of C's, but it screws up your O's. And if you keep going back and forth, it's going to be a real hard time rather than regular balancing. Plus, you also have to take into account balancing charges. And right now, it seems pretty hard to notice that there are 3 negatives on the left and 2 charges on the right. And how would you balance that? So the way we're going to do this on paper only is to separate the oxidation half reaction from the reduction half. What element's oxidizing from which element is reducing. So these are the rules, and I recommend writing them down. You're going to assign oxidation numbers to determine which oxidizes or reduces. Write oxidation and reduction half reactions using the whole compound. And then balance each half reaction following these things. So again, you might want to pause this and write this down or take a picture. You're going to balance elements other than H's and O's. All elements like copper and manganese and anything else that you want. Balance the O's by adding water. Balance the H's by adding hydrogen ions because we're going to be balancing in acidic conditions first. And so there will always be hydrogen ions present if it's in an acidic condition. And then balance the charge by adding negative electrons, right? So electrons to a certain side. Multiply the half reactions by integers like 1, 2, 3, or 4 so that the electrons gained are the same as electrons lost. You can't just lose electrons to the atmosphere. It has to be transferred perfectly. And then you're going to add the reactions back together, subtracting things that are appearing on both sides, kind of like Hess's law. And then make sure the equation's balanced, so just a double check. It seems like a lot, and it'll get easier as we do examples. So here's the first example. Considering that reaction we saw before that was really hard to balance normally, we're going to separate it into 2 half reactions. The first one thing I did was put the charges in. In MnO4 minus, O has to be -2, and so Mn, in order to net the minus charge, has to be +7 because it's -2 times 4, and you want to have a negative O left over. In C2O4 minus 2, the carbon has to be plus 3 because, again, oxygen's minus 2, and there are 4 of them. That's minus 8. You want to have 2 left over, so you only need to have positive 6. Each carbon is 3. Manganese was told to you as plus 2, and then in CO2, since oxygen's minus 2, carbon's plus 4. What you'll see is manganese goes from plus 7 to plus 2. That means it's reduced. And carbon goes from plus 3 to plus 4, which means it oxidized. So I identified which one was which. It really doesn't matter for what we're about to do, but they could ask you it on a test, which one's oxidized and reduced. So this was just a review. And so I took one of the half reactions, the oxidation 1/2. It doesn't matter which one you do first. And the first thing I'm going to do is balance the irregular elements. So to balance the carbon, we're adding a coefficient of 2 in front of CO2, which will also actually balance my oxygens by accident. And so since the oxygens are balanced as well, I'm going to skip all the way over to balancing the charge because I don't need any hydrogens or waters. So if I look on the left, I have 2 minuses, and on the right, I have 0 charge. So I'm going to add 2 electrons to balance the charge on the right, so it's 2 left negatives and 2 right negatives. And that's the whole half reaction there, so it could be really easy. Here's a little trickier one. MnO4 minus goes to Mn plus 2. I would check to make sure my manganese is balanced first, which it is. So next, I would balance my oxygens. We're going to add 4 water molecules to the right side because where there are ions, there's always water, right? 4 water so that matches the 4 oxygens on the left. Because we did that, we just screwed up our hydrogens. There's no way to balance them the way it's written. So we're going to add an additional 8 H pluses, because we said we were going to balance it in an acidic reaction, 8 H pluses to the left side. And that way, it will balance the amount of 8 H's and 8 H's on both sides. The last thing we need to do is check our charges. Because I have 8 positives and a negative manganese per manganate, that means I have 7 pluses on the left, the reactant side, and I have 2 pluses on the right because the water is not charged. In that case, I need to add only electrons. I can't add positive things. Electrons are what's changing in this reaction, so I can only add negative electrons. They're going to go to the more positive side, which in this case is the left, which is not surprising because we just said this is the reduction half, and in reduction you gain electrons. So we're going to gain electrons on the left by adding 5 electrons to that left side, and that balances this half reaction. So now that I have both half reactions balanced, I need to sum them back up. So I just rewrote them. These are the 2 that we just figured out. And before I sum them, I got to check my electrons. If you notice, there are 2 electrons lost in the carbon example, but 5 gained in the manganese example. This cannot happen. You can't lose 2 but gain 5 somehow magically. So what we're going to do is make them both 10 because that's the lowest common multiple of 2 and 5. So in order to get the same number of electrons, we're just multiplying them out. And I would suggest to do what I just did. I actually changed the coefficient. So I multiply the first reaction by 5 C2O4 minus 2s, 10 CO2s, and 10 electrons, and I multiply the second reaction by 2. You don't have to rewrite the whole thing. I mean, I'm on a computer program, so it was easier for me to rewrite it. You could just cross them out if you want, or use pencil. Now, the 10 electrons on the right will cancel with the 10 electrons on the left, and everything else will be summed together. So you could think of it this way, where the electrons will cancel on either side, and then rewrite it, or I just cancel them from the get-go and skip right to the second reaction. This is a balanced reaction. Would you have gotten there without this method? I highly, highly doubt it. Are there maybe tricks to certain reactions? Certain reactions? Sure. But this way that I'm asking you to do it is the way that will work for every reaction. So let's do this again. Make sure it's balanced when you're done, like H's, H's, MN's, MN's, C, C. We're good, right? So the second example I'm going to do is going to follow the same exact pattern, but we're going to do it in a basic solution. And then you're going to try a whole bunch of examples in your packet of balancing. And by the end of the packet, you should be good. Right now, it might be a little confusing. You might have to rewind and watch parts over again. So if a reaction occurs in a balanced basic solution, you're going to balance as if it occurred in an acidic solution. And once the equation is balanced for a mass, you'll add hydroxides to each side to neutralize the hydrogen ions. Because we said it's basic, there has to be OH ions, not hydrogen ions. And notice it says to both sides, to each side to neutralize the H and create water in its place. So I'm going to show you exactly what that looks like. If it produces a water on both sides, you might have to do a little bit more canceling on both sides to make sure you only have water on one side. So here's another example, but we're going to balance this in a basic solution. So we're going to take a half reaction like MnO4 minus makes MnO2. I know that's one of my halves because they both have manganese. I'm going to balance for manganese, which it already is. I'm going to balance for oxygens by adding 2 waters to the right side because I needed 2 more oxygens. Remember, I had 4 on the left and 2 on the right, so I need 2 more oxygens. Because I did that, the H's are off, so I have 2 times 2, or 4 H's on the right. I'll need to have 4 H pluses on the left. And this is exactly what we just did with the previous example. The only difference is because it's acidic, a basic, we don't want acids. Right? We don't want H+. So I'm going to add as many hydrogens as I have in that number of hydroxides, but to both sides. So notice that the 4 OHs are on both sides right now. What that would mean for the left side is that the 4 OHs would actually combine with the 4 H+, and it would make 4 waters. And according to that idea, if there's 4 waters on the left and 2 waters on the right, I have too many waters, so I'm actually going to cancel out the 2 waters on the right with the 2 waters on the left, and that's what this reaction should look like now. That's a lot of pointing, crossing things out. I really recommend pencil because it might be easier than rewriting the way I am. And then to move on, we need to do our last check of balancing charges. So on the left right now, I have 2 waters, which are neutral, and a permanganate ion, which is minus. So I have minus on the left. And I have 4 hydroxides negative on the right. So I need 3 more electrons on the left in order to have 4 negatives on the left and 4 negatives on the right. Remember, you are only allowed to add electrons that are negative to the more positive or less negative side. The other half reaction was the cyanide reaction, because they both have C and N. C and N are balanced, so I don't have to do any balancing there. I really recommend you check that first because a lot of people miss that on the examples. We're going to add water to the left because I had an O on the right, so I need an O on the left. And because of that water, I need to add 2 hydrogens on the right to balance the amount of hydrogens. So your options are to add waters, hydrogens, and then in basic solutions, hydroxides. Since I added 2 hydrogens on the right, I'm going to add 2 hydroxides, but to both sides, because I want to cancel the hydrogens. So I cancel the hydrogens with the hydroxides to make 2 waters. Watch out, because now there's water on both sides, so you might want to cancel that out. Let me back a step there. So now the 1 water on the left cancels with 1 of the waters on the right. You're not seeing that cancel yet. It'll come up. I just had my things coming up at the wrong time, sorry. And then I added 2 electrons to the left because I had 2 negatives and a negative, 3 negatives on the left. And on the right, I only had 1 negative, so I needed 2 more negatives. Now what we'll notice is that there are 3 electrons being gained, but somehow only 2 electrons being lost. So that's why I did this, this parentheses thing, where I multiplied the whole of the bottom reaction by 3 and the whole top reaction by 2. That's another way of showing what we saw in the previous example. I don't recommend this way because a lot of people make mistakes. They forget to carry it through. I recommended to actually change all your coefficients, but it really doesn't matter if you're showing your work this way. So in that case, the electrons will cancel, but some other things will actually cancel as well. Some of the waters will cancel out because now I have like 4 waters on the left and 6 waters on the right. So you have to just do some canceling and some finagling around. I'm sorry, I had 8 waters on the left. 4. Yeah, I don't know. It got kind of crazy, and this is why I don't recommend doing it this way. I recommend actually changing all your coefficients. So at the end of the day, you should have 2 MnO4s, we multiplied by 2, 3 cyanides, remember we multiplied by 3, 3 CNOs, which we multiplied. See, some people would miss that one if you're not checking it. 2 MnO4s, we multiplied by 2. Only 2 hydroxides on the right when some of them canceled out, and a water on the left. And if you double check, that means that for each H on the left, you should have an H on the right, 2 H's, 2 H's. 1 O plus 8 O's is 9, 3, and another 4 and 2 there is 9. 2 MNs, 2 MNs, 3 C's, 3 C's, 3 N's, 3 N's, and also charge 2 minuses and 3 minuses is 5 minuses on the left, 3 minuses and 2 minuses is 5 minuses on the right. I would never have gotten that from what I got if I didn't do this method. So at this point, you should be identifying oxidizing and reducing elements as well as agents and balancing acidic and basic solutions.